Good morning. Yeah, good morning, everyone. Yeah, so as we discussed yesterday, just I'll share my screen. Please wait.
Good morning, Chandra sir.
Yeah, good morning. Good morning, sir.
Very good morning, sir. Sir, you can start the session, sir.
Yeah. I'll start the session. Thank you.
Thank you very much, sir.
Okay.
I request the participant please cooperate. You ask the doubts at the end of the session.
No, I'll do that. I'll manage that. Yeah, Praveen sir. Yeah, I'll do that.
Thank you,
Okay.
sir. Thank you.
Right. Yeah, yesterday we completed CNN portion. Now, today we are going to discuss RNN part. And before going to RNN, first we are going to discuss the limitations of CNN. Please respond. My voice is clear and my screen is visible. I hope so. Please respond yes. Yes. Thank you, ma'am. Right. So today, first we will discuss what are the advantages with the CNN. Yesterday we discussed the CNN. We can call it as convolution neural network or convnet also is able to successfully capture spatial and temporal dependencies. And yesterday I differentiated why we go for deep learning. Two advantages we discussed. Along with those advantages, machine learning model or machine learning technique we can use for what we can say static data. Like we have already data set, we can prepare a model on the data set and we can test the model. That we can do it. Suppose consider one scenario where data will generate, like IoT applications. You take it through sensors, we can get data very frequently. Like in some applications we'll get within seconds, and in some applications we'll get so per day we will get it. So in such dynamic data generation applications where data can generate temporally, okay, so in such applications we will go for deep learning. Our deep learning model we can means we can enhance our model, we can train our model dynamically. In such scenarios we will go for deep learning. Now See here, advantages of CNN. If you go, the weights are smaller because you when you compare with the artificial neural network, that multi-layer perceptron, we have to train lakhs of weights, or we have to update lakhs of weights. So here in this case, only few kernels will take it, like 64 into like 5 by 5 kernel. If you take it 64 into 25, 64 into 25, how much? Very small number of weights we can update it. Very small number of weights we can update it. That is the advantage we'll get with the CNN. The weights are smaller, shared. Moreover, we can share data, and less wasteful, easier to train than MLP. Okay, we can easily train with. So more effective too. Can go deeper also. In CNN we will go deep and deeper. Now layers are sparsely connected rather than fully connected. This is another advantage. In fully connected, what we see, all layers are connected in fully connected fashion. But here, from convolution to max pooling, if you go, we reduce so many features. Okay, all connections are not fully connected, sparsely connected in CNNs. Now the major drawbacks of CNN are, so long-term dependency problem. The long-term dependency problem is, suppose, just to take one example, I'll explain that long-term dependency problem clearly. So suppose the output is depending on the previously long back given input. So such a type of dependencies, if there, the CNN can't solve such issues. So I'll explain. I'll go in detail about long-term dependency. Now black boxes. What is the black box? CNN extracting features. Which type of features we don't know. CNN can extract from raw data. It can extract features. It will, from images it can extract objects, but which objects it is extracted, it will not disclose. It will not disclose to us. That we can say black boxes or magic boxes. These two problems are there. To solve this black box concept, interpretability came into picture. Now to solve this long-term dependency problem, RNNs we are using. Then we'll go for RNNs now. So recurrent neural network. So we are introducing first what is RNN, recurrent neural network. How can we train RNN? Now types of RNN. Then we will go for one special case of RNN, that is LSTM. And if time permits, we'll go for case study, because I have only 1.5 hour session now. Now, what is the necessity of RNNs? What is the importance? Why we require RNNs? CNNs works for image data effectively. CNN works for image data effectively. What if input is sequence of words? Just consider input is sequence of words. You are going to predict next word. You are going to predict next word. Suppose image data we can convert into numbers, and we will extract features. CNN can extract features and classify or predict class labels for a image. Now think, if data is text data, now see, sentiment analysis. Please listen carefully. These are different research applications. All are different research applications. Sentiment analysis, I told you previously, sentiment analysis means, for suppose in the pandemic scenario, how people are, like, what is the sentiment about something. Suppose government given one scheme, okay, released one scheme. About that scheme, if some people are writing blogs, so they want to know how, whether the people are happy or not, whether the people are happy, whether they are satisfied or not. So that comes under sentiment. Or some particular products or particular something, okay, whether the people are in positive opinion or negative opinion. So in that Based on the text, we can analyze it. Based on the text, we can analyze it. That comes under sentiment analysis in natural language processing. This is a subpart of natural language processing. Now, time series data. Now, time series data means like take Indian stock market. Okay, data will generate based on time. This hour, what is the stock value? Next hour, what is the stock value? In such scenarios, how can we predict it? Okay, CNN can't predict properly. We will go for RNN. Now, machine translation. Machine translation means you take from one language to other language. Suppose if you want to communicate with some Japanese, okay, so you know only English. Maybe they don't know English, that other end person, they don't know English. That machine translation, one device is there, you just speak in English, that will convert into Japanese, and when the person can respond in Japanese, it will convert to English and give to us. Such machine translations, I think recently some videos released in YouTube. Maybe some of the people saw those videos. When we communicate with other person, they don't know what are the languages we know, then this machine translation plays a key role. In machine translation also, machine translation means first the model can read the understand the whole sentence what I can speak, then it will convert into that language. Okay, then when the other end person can speak, it will convert into my language. That machine translation, in such scenarios also RNNs works better. Now, speech recognition. Speech recognition means, yeah, see, when you speak, then just nowadays in mobile phones also, when you open YouTube or any app, there is a option, speaker option. When you press it and if you speak it, that it will convert into text speech. Whatever the audio file you send, audio you give as input, it will convert into text. When we want to search in Google, yeah, directly if I say something, it will convert into text and it will search it. In such a speech recognition applications also, RNNs works better. Now, image captioning. Suppose if I give any image to the model will describe about that image. Suppose if I give any image related to a park, so my model will give like this picture related to park, and children are playing in the park, and some elders are like doing exercises or doing jogging. So such sentences it will produce by looking the image. So in such applications also, the RNNs works better than the CNN. Now, what is the core idea of RNNs? If you go it, if outputs, see this long-term dependency problem I'm explaining now. If output depends on sequence of inputs, then we have to build a new type of neural network that can retain sequence information. Here, the main thing is it needs to remember something. Whatever the input we pass to the model needs to remember that input. Then only it can satisfy the long-term dependency problem. So the RNN can do that. It can retain some information. It can retain sequence information. Just to take simple example, the phone is very dash. So this, forget about this fast word. We given one sentence to the model. How? Like this, the phone is very dash. We need to predict a word. Okay, we need to predict a word. Generally, as a human being, what word we can keep here? The phone is very like fast or very good. The phone is very bad, or the phone is lightweight. Very, when very comes something, we have to only few words we can predict it as a human being. How machine can predict it? That we can see with long-term dependency. In long-term dependency, that RNN can remember the previous words information. Like phone, generally phone means it's a device. For device, And phone and very, these two words, by looking these two words, it can predict, yeah, the phone is very good or very bad or very like what we can say, very fast. Okay, like that. Now take one more example. The movie is very dash. So the movie is very dash. In that case, we can't predict the movie is very fast. We will not say like that. The movie is very good or very bad. So like some words we can predict it. Some words we can predict it. Mostly, to predict this fast word, it is depending on two words. Very, one is on very and another one is on phone. It is not depending on the and is word. So like this, it will remember the previous words information. It can retain the some words information which are play crucial role to predict next word. So it will remember, and then based on the previous remembering words, it can predict the next word. Okay, now if we use neural networks for this task, if we use neural network for this task, the input size is different and massive networks. We have to design massive networks. RNNs can solve these problems, these long-term dependency problems. Now, recurrent neural network, RNNs. Now, how RNN, recurrent neural network, works? RNNs are networks with loops. RNNs are networks with loops. What's the meaning of this? Just look this diagram. So this A is there. This is my RNN. Just imagine this is my RNN. Now, how it works? It will take input. See, RNNs means related to time. Okay. So at time t0, it will take input xt or x0. Just imagine x0. It will generate some output, intermediate output. The same output it will pass to the same model. Next, at a time t equal to 1 instance, it will take x1 and it will take previous output ht minus 1, previous h0 output, it will take it and it will generate h1. Suppose the same model is like this. Recursion, if you have any idea about recursion, what we can do, we can invoke the same model. In the same way, here also we are doing same thing. So now time t equal to 0, time t equal to 1, time t equal to 2, and time t equal to some n. See, if you unroll it means at time instances how the model look like. So it will take at time t equal to 0, it will take x0 input and it will predict output. There is no previous output. So at time t equal to 1 instance, it will take x1 and the previous output, whatever h0 generated, the same output it will take it. By using this output and current input, it will generate output, and so on and so on. Finally, it will generate some output, right? So RNNs are new networks with loops allowing information to persist. Suppose whatever the information you passed here at x0, it can remember it because we are sending the output. Okay, we are sending the output and it can remember it. Now the phone is very fast. Same example, you take it. Now I'll convert this word the into numerical vector. I'll pass here. The phone I'll pass here. Is word is passed here, and next very we will pass here, and finally it will generate a word. Okay, numerical vector. A numerical vector. By that numerical vector, we can predict this word fast. We can predict this word fast. So how can we convert words into numerical vectors? All those we will see further, right? So word to vec, one concept is there. That word to vec, it will convert words, given words, into numerical vectors. That is one concept. And when there is one more procedure, we can create our own procedure to generate words, to generate numerical vectors for corresponding words. Yeah, that we will see further. A RNN can be thought as a multiple copies of the same network. Yes or no? So don't think this is the network. Only this is the network actually. For our understanding purpose, I unrolled it. That's it. So this is actual network. So multiple copies of the same network, each passing a message to the successor. Yeah. At the time T naught, the same model pass to the output to next time T1 model. Model is same at a time T1 instance. Whatever the input it is taking, current input, previous output also it will take it. Now where we are using? In bioinformatics, we are using RNNs, computational biology, machine translation, speech recognition, language modeling, image captioning, etc. Whatever the application we discussed, in all application we use this. Now come to long-term dependency problem. Okay, suppose the word here what we are predicting at a time t equal to 3, whatever the output we are predicting, that output is depending on the previous inputs. Okay, this x0, x1. So like the clouds are in the dash. So generally the word is sky. How we are predicting? Please check the sky word we can predict by depending on which word clouds. By depending on which word clouds. So remaining in the also these two words also plays a little key role, but majorly the clouds word play a crucial role to predict the sky. So this type of problem we can say long-term dependency problem. Now come back here. So RNNs, take one more like sentence, like I told you, like I born and brought up in Hyderabad. I completed my schooling in Hyderabad, right? Then I went for higher studies to Calcutta. Then I did my job in Pune. Then uh, I'm working, okay, now in Andhra Pradesh, like that I told you. Now finally, I speak fluent to dash. If I say like that, I studied in Calcutta, means maybe I know Bengali. I worked in Pune, means maybe I know Marathi, but I can speak fluent to dash means generally, very commonly, the person where he born and brought up, that language he can speak fluently. Most of the cases, or some special cases are there anyhow. Most of the cases. So uh, I can speak fluent Telugu. Okay, this word, that Telugu language we can predict. To predict this word, we need to check on which we are depending on where you born. Hyderabad. So Hyderabad means, yeah, which language? Telugu. So generally such predictions we can do in these sentences. So many sentences are there, and somewhere we are predicting some word. Here dependency, we are depending long back inputs. Now RNNs are absolutely capable of handling such long-term dependencies theoretically, but not in practical. Who will solve this problem? LSTMs can solve this problem. We will go to LSTM later. Before that, we will see how recurrent neural network works. Okay. Now consider reviews of Amazon. So Amazon, one IMDb data set is there. So that is movie reviews. It contains movie reviews. So it is a binary classification problem, whether the movie is a good or a good means whether the movie got positive review or negative review. That was there in that. Suppose you just consider one review, one person given one review. So that data set contains, just I'll go. So the data set contains, yeah. 1 to I think 50,000, 50K reviews it contains. 50K reviews it contains. This is a sentence. This is one sentence. This is one sentence, and this is another sentence. So what that sentence contains? Sentence means text. It contains a text, and they prepared reviews, labels. So this is positive. Positive means 1, negative means 0, 1 1 0 and so on, 1, like this. It is there. The data set contains total. So this text also, this whatever the text I said, the text also not fixed length, variable length. Some may given review in 150 words, some may given review in 500 words, some may given review in 1000 words. Yeah, like that, different people given different reviews. So here it contains reviews only. If some is there, someone is given very big review, like that, all statements we have. So in this is X, means review. This is Y, means label, corresponding label that represents here. So D equal to XI YI, where XI is sentence, YI is binary label. Okay, XI is sentence. Now if you go to sentence, you take one sentence, any one sentence, that sentence contains different words. That sentence contains different words. Suppose the movie is very good, like this. The movie is very good, very good, like this. One sentence is there. So the movie is very good. So in this sentence, how many words are there? This sentence is my X1 sentence. How many words are there? This is first word, second word, third word, fourth word, and fifth word. So this one I'll consider like X11, X12, X13, now X14, and so on, X15, and so on. Yeah. So this is, suppose X1 is X11. These are words, and corresponding label is either 0 or 1. Okay. Now words are converted to one hat in one hat vectors. Each word in a sentence is converted into one hat vectors over a vocabulary of dimension D. Suppose, how can we do this? Suppose the whole movie review contains 50,000 sentences. If you consider 50,000 sentences, in 50,000 sentences, there are near about, just imagine 10,000 unique words are there. Unique words, 10,000 unique words are there. So what I'll do, 10,000 unique words means each word, first rank I'll calculate, frequency I'll calculate it. Based on the frequency, I'll give ranks to each word. By using that rank, we can convert it to numerical vector. That I'll discuss later. So in that way, we can convert each word into numerical vector. Now see this here, the example of RNN, how it will work. Suppose here we given one first word, X11 word in numerical vector, X1 word in numerical format. I given here, this link has a weight associated, and this is my model, and it will generate output O1. How can we write O1? O1 equal to, I think I will keep full screen mode. Yeah, O1 equal to this function. This is my model, means it's a function, some mathematical operations it will perform, some function of W into X1, 1, W into X11. So this weight and the numerical vector we can multiply, and we will give this value as an input to this function. It will generate some output. Now next time I'll give X12. So here previous output we will sending to current model. So here W dash is there. Weight is associated to this link is double dash. Weight is associated to this input link is W. Now how can we predict output? O2 is equal to F of W into X12, this plus double dash into O1. Okay, in this way we can calculate, and so on we will do it. Finally, if words all are completed, the output it is generated. That output we will send via softmax function. Lastly, we have a softmax function. So that softmax function will predict some value, like suppose 0.6 we got it. So what we will consider, it is close to our threshold is 0.5. Just imagine, above positive review, below negative review. 0.6 if you got it, so we'll consider that that is a positive review, like that we can train the model. Now see how here output O5, if you observe here, one weight is associated, double dash. So how many types of weights are there? W, double dash, W dash, and double dash. So total 3 types of weights are there. Via back propagation, we can update weights at the time of training. Okay, at the time of training. If you observe any CNN or any neural network model, we can, at the time of training, we can update the weights. In artificial neural networks like MLP, we can update weights. In convolution neural network, we can update values in kernels. Here in RNNs, we can update these weights. Now training recurrent neural network. So just to take this model, actually I'm inside how it look like. See, this is a this addition. Okay, what we can say, numerical, not numerical, binary, not vector addition. Actually this is vector addition. So this value output is in vector format, this our input is in vector format. We can perform addition, vector addition, and we will pass the result to this function and it will generate output. And suppose if you want to predict here intermediate output, we will pass via some softmax function, it will predict value. Whatever this output is there, we will pass it. The same model, how can we represent like this? So this is RNN. Again the output goes to the same model. Okay, box representation we can say. So how can we train in back propagation? Means, see, we will find loss function, will perform partial differentiation of loss function with respect to all these 3 types of weights, and we can update the weights. So see, these are the mathematical representation of O1, O2. Here O1, O2, O3 all look like. Next, how can we perform partial differentiation? Dou L by dou double power double 1 is equal to dou L by dou yi. Just wait. Yeah, if you perform this, dou L by dou yi and dou yi by dou double dash, and if you want to do with respect to this weight, with respect to that weight, dou L by dou yi into dou yi by dou O10 and dou O10 by, like this, with respect to this weight, with respect to this weight, with respect to all weights, we can perform partial differentiation and we can update the weights. Now, so finally we have all these partial differentiation values are there, and we can update those weights, So just go through this slide. Now come to types of RNNs. What are the different types of recurrent neural networks we have? So there are generally in functions in maths, we have one-to-one function, one-to-many, many-to-one, many-to-many functions concept is there. Same way here, recurrent neural networks. There are 4 categories of recurrent neural networks. One is one-to-one, one-to-many, or many-to-one, and many-to-many, and many-to-many. So many-to-many, 2 categories are there. We'll discuss one by one. One-to-one means, suppose if I give one input, the corresponding output it will generate it. In real time, this one is not useful. Generally, we will not use, but this one we use in different format. We will see that. Now come to one-to-many. Suppose if you give one input, it will generate multiple outputs. I discussed the multiple examples previously. There, just correlate here and type me in chat box. So which concept, in which concept we use this one-to-many RNN? Anyone please type in chat box. Image captioning. Okay, in image captioning, what is happening? I'll give one image, it will predict multiple words or multiple sentences, multiple music generation. Music generation maybe. Okay, music generation means how I don't know, but maybe there is a possibility. So image captioning, if you give image multiple words or multiple sentences, it will generate it. Now come to this case, many to one case. In many to one case, tell me one example where we use this many to one case. Same movie review. So suppose if you give no language translation, it will not work one to many. So this one also not work in language translation. Suppose here if you see, if you give multiple words, finally it will generate one output. Okay, suppose product rating, yeah, comes this category, many to one category. So our movie reviews, sentiment analysis, all comes this category, many to one category. Now many to many, two variations are there. In the first variation, see, all inputs we will pass. After completion of, after passing last input, the output starts generating. In this one is useful in machine translation. Suppose if you give English sentence to convert into Telugu sentence, first we need to read whole sentence, English sentence, word by word. If you convert it, it not proper. We will not generate proper sentence. Okay, we will not generate proper sentence. So in where it is useful in machine translation. Now come to many to many. Suppose where it is useful, many to many. In this case, for every word it is generating output. So where it is useful means in parts of speech recognition. See, if you give in one word corresponding the, okay, the word is article, uh, movie, okay, corresponding something, okay, and movie is article, like that. For every word, the part of speech it will generate it. So based on your application, we have to use these types of RNNs. Which RNN is suitable for your application, you use that RNN. Now go to modified RNN. Modified RNN means in modified RNN what we will do here, vector addition we are doing. Instead of that, we will perform vector concatenation. Okay, that becomes another type of RNN. That becomes another type of RNN. So vector concatenation, when vector concatenation, so we will take output, previous state output and current state input, and we can concatenate it. What is the difference between vector addition and vector concatenation? If you see, this is my simple vectors, I'll take it. Okay, so this is first vector 0.1 v1 comma 0.5. This is simple vector. Another vector, just take 1.5 0.9, like this are there. In vector addition, what we will do, how can we generate vector addition? We will generate output, that is, will combine these two, or we will add 1.6 and 1.4, it will generate. In case of concatenation, this is addition. In case of concatenation, it will generate 4 length output. So first I'll put 0.1 comma 0.5 comma 1.5 comma 0.9, like this it will generate it. Like this it will generate this vector. If you put, see, small modification, we are generating new type of recurrent neural network. So concatenation we can use like this. So this is modified RNN. Now you just observe here, in addition, double into x1t plus double dash into ot minus 1, like this. So in case of this, f of double comma double dash comma dot x12 comma ot1. So here we are doing like this. These two we are concatenating separately. These two we are concatenating separately. So this is the way we can modify one RN into other RN. Now come to LSTM. Quickly I'll go through LSTM, then we will go for one example. So LSTM, long short term memory. in long short-term memory, LSTMs are a special kind of RNNs which works much better than the standard version. So see this, this LSTM, this is my model. Okay, I'm repeating the same model to represent to show. Okay, so at a time t minus 1 instance, this is my model. At a time instance, same model only, but here internal structure I shown. At a time t plus 1, this is the same model only. At a time t minus 1, it will generate ht minus 1. So here, along with output, we are passing one more also, that is cell state. We can call it as cell state. We are passing through the cell state. We can remember previous states input. We can remember previous states input. Are you people following? Please respond yes or no in chat box. Okay, good. Everyone saying. Yeah. Now, LSTMs explicitly designed to avoid long-term dependency problem. I told you, capable of learning order dependency in sequence prediction problems. In the sequence prediction problems, you can remember orders dependency. Okay, order dependency. Now, first I'll explain what it contains. So see this yellow type, yellow boxes, rectangular boxes. These are, we can say, trained neural networks. This sigma function, sigmoid activation function is shown, but these are trained convolution neural networks. Finally, at output, we used sigmoid activation function. Here also sigmoid activation. Here tan H. Here sigmoid activation function. Now this circles, if you see 3 circles, 4 circles are there. In some circles int mark is there, some circle plus mark is there. These are used to perform vector addition and concatenation, vector addition and multiplication. Now here tan H is there. Okay. Now finally it is generating HT. It is taking input. It is generating 2 output. One is cell state, another one is output. Okay, it is passing to next layer. Now see, this is a neural network. The yellow boxes are learned neural network layers. There's point-wise operations. Line carries, this line carries entire vector from output of one node to inputs to other. This represent concatenation. 2 vectors I am concatenating. This represent, this fork means the same vector will go into different directions. Okay. So now come to one by one. Please listen here carefully. In LSTM, by looking code will not understand anything. Okay. In LSTMs, by looking code will not understanding anything. So what we will, how we can understand? First, we need to understand background, right? See how what is there inside. If you know that, will imagine at least how output will generate it. See, this is my cell state. First, A you just look it. In this, the upper line, if you observe, upper straight line, if you observe, this line represent like this. That is cell state. What is the importance of the cell state? The cell state carries previous state information to current state. Previous state information. Why it is useful? Suppose some word is very important to predict output. Okay, at some time instance t equal to 3 time instance, that word came. Okay, that word came means that word we pass to the model. So that information it will remember and it will store in cell state, and it will carry forward to the next layers, carry forward to the next means next time instance to the same model only, right? This is cell state. So the cell state is kind of like conveyor belt, so it will carry some information. In mining we use this word conveyor belt. On that they will throw coal and it will carry, means it will take that coal to some destination. In the same way it will work. So now gates are a way of optionally let information through. So here one gate is there, either here, okay, some point wise multiplication is there, point wise addition is there, vector addition is there. Now see, this cell is bringing some information, the cell is bringing some information, or come to B. This B is forget gate layer. This B represent forget gate layer. Here one neural network is there. It will generate value in between. This is sigmoid. Okay, sigmoid nonlinear activation function. I told you sigmoid nonlinear activation function generates output between 0 to 1 only. Between 0 to 1 only. What it will play crucial role. So this is the previous state output. Just come here. My this is my cell CT minus 1. Just imagine CT minus 1. So here point-wise multiplication is there. So here my sigmoid activation function is there. This we can say forget gate layer. Forget gate layer. What it will generate? It will generate value from 0 to 1. Suppose my previous output, previous cell state values are like this: 0.2, just 0.4 or 0.3. Just imagine. Okay, just imagine like this, some values we got it. What the sigmoid, what it will do, just observe this diagram. It is receiving previous state output and the current state input, and it is concatenating, and we are sending that input to the convolution neural network. It will generate some value. What it is generating? Suppose 0.5 it is generating. Just imagine 0.5 it is. Forget gate layer tells that how much information, okay, we have to remember, how much previous state information we have to remember. So here what we are doing, 0.5 it is generated. Now what we are doing, point wise multiplication we are doing. So this 0.5 into 0.2 or 0.5 into 0.4, 0.5 into 0.3, what it will generate now? See what it will generate: 0.1 comma 0.2 means 0.15 it will generate it. Okay, means half of the information, previous state, half of the information only we are remembering. Okay, now here one more gate is there, one more, what we can say, one more operation is there, that is point-wise concatenation. For this point-wise concatenation we are getting input. So I'll go to that. So see this, for this point-wise concatenation I am getting input via this sigmoid activation function, via this tan h. Again here some multiplication is going on. What it will generate? This, see, please observe my cursor, please observe my cursor. This will send how much current state information you have to remember. Previous state information we remember something. How much current word is important, or how much current input is important, that information it will give here, that information it will give here. So via sigmoid it will generate something, via tan h it will generate some vector. Here we will multiply this, we can say update, we can update it. So that I'll explain here. Suppose I got here something like some vector. Okay, the vector is 0.6, 0.9 or 0.1. This information is we are updating in current state. So we can perform concatenation. Finally what it will generate: 0.1 plus 0.6, 0.7, 0.2 in plus 0.9, that is 1.1, 0.15, 0.25, like this it will generate. Okay, in this way, this is my CT, current state cell state, current state cell value. Here you see 0.5 it is generated. means half information we remembered. Suppose when it generates 1, so 1 into this value, same output it will generate. Means whole previous input is important. When whole previous input state, when whole previous input, when previous cell state information important, it will generate 1. If you multiply with this same output, it will generate. Suppose previous state information is not at all important, it will generate 0. 0 means 0 into anything, it becomes 0. Suppose current state information is not at all important, it will generate zeros, 0 comma 0 comma 0. The current state information is very important, then it will generate ones, 1 1 1 1, like that. Okay, so for your understanding, I given these numbers, maybe something, okay, not exactly, but numerical. In the same way it will generate it, in the same way it will generate it. Now come back to our, you see here, just I'm giving here CT minus 1 is 2 3 4 5, but suppose previous cell state information is 2 3 4 5. FT means forget gate layer, means everything is important, so we can simply multiply 1 into 1, 1 into 3, 1 into 4, 1 into 5. The current state information is not at all important, so all are zeros. We can find CT. Suppose CT minus this, forget gate generated 0.5, half of the information we can remember. If input is IT 0 0 0, this is the way we can generate CT. Now forget gate layer, this forget gate layer, what is the formula? Yeah, f of t equal to sigma of WF. What is this WF? Here weight associated, WF into HT minus 1 comma XT. HT minus 1 previous state output and XT is current state input. Here we are doing concatenation plus some bias, we can add it. Okay, some bias we can add it to avoid something like some external disturbances, all the things. If we lose some data, to overcome that, some bias we can add it, some bias value we can add it. Now come to input gate layer. This input gate layer, this is the formula, tan h, this is the formula. See, everything is same. Wi into ht minus 1 comma xt plus some bias, ct minus 1 tan h double c, this is update gate. So what we are doing in update gate, ct, okay, ct, that update state ct, f of t, what is f of t? This forget gate layer into this value ct minus 1, these two we are multiplying, plus here we are adding this value. How we will get this value? IT, this value into this value we are adding. So this is the way we will generate current state output. We will generate current state output. Now come to last phase. How can we generate output? So to generate output, we prepared cell state CT. That CT value, vector value, will send via tan h. Okay, via tan h. So and one more sigmoid neural network is there. This will generate OT. We will perform this value and this value. So see, OT is equals to sigma of this, HT is equals to OT, whatever this OT generated, tan h of CT. Okay, tan h of CT. This is the way we can generate outputs. It is very, very complex, but you try to understand. Once if you understand, now by giving input, what is the output is generating, easily you can analyze it. Now come to different variations of LSTM, different variants of LSTM. Peephole LSTM. Peephole LSTM means whatever the current current previous cell state is given to this neural network as input for this neural network, and the current cell state value we will give as a input to this neural network. So this is peephole connections, we can call it as. Now formulas, just go through it. Only this part extra it will add. Now coupled forget gate and input gate LSTMs. Coupled forget gate means, so for input gate we removed. See, input gate we removed here. Whatever the forget gate generates output, that we can subtract from 1 and we are passing here. for multiplication. This type of connection we can say combined input and forget gates. One more famous LSTM is there, that is GRU, gated recurrent unit. The structure look like this. Okay, the structure look like this. So how can we generate equations? Easily, by looking this diagram we can easily generate these equations. GRU combines the forget and input gates. See, there is no forget gate and input gate, they combined it into single update gate, and also merges cell state and hidden state. Cell state and hidden state they merged. Previously it is from one state to next state. Two outputs we passed, cell state value and current previous out value, but we combined that in GRU. So these are GRUs. Now I'll go for how can we solve IMDb movie review data set. How can we what we can say classify, or how can we predict positive review or negative review of particular blog from particular blog? How can we do that? We can see now IMDb database. If you see, database of movie reviews contains review text along with its sentiment. Sentiment means positive means 1, negative means 0. I already explained about this. IMDb dataset readily available in Keras. Already at the time of MNIST dataset, we import how we did from Keras datasets import MNIST. We did it in the same way. Here also we can import this IMDb dataset. Now, what is Keras? Is a open source neural network library written in Python. Okay, about that, about Keras. Now come to this movie reviews. Suppose 50K reviews split into training and test set. So 50K reviews are there. Total 50K reviews are there. 50,000 reviews are there. From 50,000 reviews, they splitted training and test set. So now see 1 to 50K. These are the labels, class labels, 0, 1, and so on, 1. So splitted 25, okay, for training and testing. This is for testing. This part is for testing. Now, how we can convert numerical vector into numerical, how can we convert words into numerical vector? You see, I told you in the 50,000 reviews, just imagine total 10,000 unique words are there. 10,000 unique words. Okay. Now I'll calculate those 10,000 unique words of frequency. How many number of times that word is repeated in the whole 50,000 reviews. So I just kept, for example, I kept like this. So the word the 49,000 times it is repeated. Next to movie word repeated 45,000 times. Is 25,000. Very 15,000. Good 6,000. Like this. So total each and every word frequency I'll calculate, and I'll arrange the words in the decreasing order of their frequency. Okay, decreasing order of their frequency. Now I given rank 1, 2, 3, 4, and so on. The highest word, highest frequency word rank is 1, and so on, like this. Suppose if you take this word, the movie is very good. How can we represent that word? 1 rank, with respect to rank I can represent it. 1 is the, 2 means movie, 65 means is, 89 means very, 189 means good. So are you people followed till now? Please respond. Yes, fine, good. Then suppose in a sentence, suppose 150 words are there. Each word rank we can write it. Each word rank we can write it. Now go to next. Suppose this x1 is 189 words are there. x2 250 words are there. x3 150 words are there. Now what we will do, all each and every sentence I'll convert it into 600 length. Fixed length I can make it. To do fixed length, what we will do, we will do pre-padding. Some zeros I'll add it. Okay, suppose 189 words are there. 189 words, 18, each word contains one rank. Suppose I'll consider only top 5,000 words only. Remaining words I'll skip it. Remaining words I'll skip it. Meaning is, suppose any word rank is below 5,000. Okay, below 5,000 means 5,001, 5,002, and so on. Then I'll, for that word rank, I'll keep 0. That word rank I'll keep 0. Right now, to make 600 length, I'll do pre-padding. Why I'm doing pre-padding? Why not post-padding? Pre-padding, if you do it, if you do post-padding, to predict some word, we have to keep information of long backwards. Instead of that, if you keep zeros here, lastly if you keep words, so to predict some word, we need to depend only recently words. Means recently means from here only. Instead of checking previous 600 or 500 at the word, we will check up to here only, right? So that padding converts each review same length, 600 length, we can review it. Generally, at the time of passing, one word vector we will not send. 5 or 10 movies reviews we can send at a time. Okay, 10 movies. Suppose here for this model, I'll send first, these 3 sentences are there. First words of 3 sentences I'll pass here. Next, second words of these sentences I'll pass here. Total each and every word length is 600. So 600 times we can pass it. Finally, it will predict some value, that based on that value by loss function, we can predict whether the movie review is positive or not. So the model architecture, if you observe, so this is my embedding layer. How many layers are there total? LSTM layers. This is my embedding layer. Why we use embedding layer means each yeah, see, yeah, this word is there, these numbers are there, these numbers, whatever these numbers are there, these numbers again we can convert into 32 length vector by using embedding layer. See, embedding layer turns positive integer into dense vector of fixed size. Suppose you take 1 0 is there, 2 words are there, first word rank is 1, second word rank is 20. How can we convert into numerical vector? Like this. 1 I represent like this, 0.25 comma 0.1, and 20 I can represent minus 0.5 comma 0.7. Who will do that? Embedding layer can do that. So here, how many LSTM layers I took? 100 LSTM layers. 100 LSTM means not this is 1 2 3, not like this. This is only one LSTM. Okay, but repeated multiple number of times. Such LSTMs I'll take 100. Better I have one diagram in next slides. Yeah, like this. So this is my one LSTM. This is another LSTM. Next another LSTM, another LSTM, like 100 depth. The depth we can call it as this depth wise 100 LSTMs we can take it. Not this one. This how many times we can do? 600 words are there. So 600 times we can repeat it. So this direction means 600 times we can do. This direction 100 times we can do. 100 times we can do. Right, 100 LSTMs. It will generate 100 outputs. By using sigmoid, we can predict values for each sentence. So this, how can we execute it? I'll go and show you one example. See, Google Colab. Now see this. This is simply like how can we import model, different packages, data sets, IMDb, model, sequential, layers, dense layer, layers, LSTM layer, from layers embedding, we are importing embedding layer, from pre-processing sequence we can do all this. Okay, I imported. Now I'm loading top words 5,000 words only I'm considering. Top words means those words rank is frequencies, uh, in frequency, we arranged in frequency order. Only those top 5,000 words we consider. Now we are importing those words only in a sentence. If the word rank is 5001, we can skip that word, right? So we imported xtrain, ytrain yesterday in amnesty dataset. How we imported, in the same way we did this. Now we are, see, I'm printing x train of 10. How it look like? Yeah, see this ranks, you see each word rank, you see 1 785 189. So up to 5,000 only we took it. So 3,000 rank, now 2,068 rank, each word ranks displayed. Now which type it is? List. And how many words are there? Length of extrain means 450 words are there. Remaining 150 zeros we can prepare here. Each sentence, rank I took it. Okay, rank I took it. Now max review length 600. Please pad it. How can we pad it? Now 10, you see I'm printing 10th one. So see, first 150 words are like zeros, remaining are like this. Total 600 ranks are there. Each sentence is converted like this. Are you people following? Please respond yes or no. Yes. Yeah. Total, how many uh, sentences we have? Total 50,000 sentences are there. Each sentence is converted like this. Okay. Now this is the model. See, model is very only 6 lines. That's it. Embedding vector length. Each word in this, each number is converted to 32 length vector again. Okay, that we can do via embedding. So embedding vector length is 32. Model is sequential. Model dot add. First we will add embedding, because you see, first we will add embedding layer. Top words only, top 5,000 words only we are considering. Embedding vector length is 32. Input length is max movie length 600. Now model dot add LSTM, 100 LSTMs I'm adding. Finally, one dense layer I'm taking. Activation function is sigmoid. So compilation, binary cross entropy we used previously in case of MNEST dataset in CNN. We used what categorical cross entropy, because we are classifying into 10 groups. Now here we are classifying into 2 groups only, whether the movie is positive or negative review. Okay, binary class. That's why binary cross entropy last function we used. Optimizer Adam, metrics accuracy. Already we saw all this. What is the meaning of this? Now model summary. If you want, you display it. Next, model dot fit. Xtrain, Ytrain will take it. Validation Xtest, Ytest. Epoch 10, batch size 64. Okay, total 25,000 sequences I'm taking. In each batch, 64 sequences we are keeping. So this is the way we can do it. Just run it. It will take some time, I think so. 10 epochs. Yeah, it will run. Meanwhile, yeah, go for question answering. We will go for question answering. First, please, I'll check chat box first. Is there any questions written here? How did you convert 1 and 20? Oh, How did you convert 1 and 20? See, sir, here, for example, I kept that. See, this one, these numbers are there. These numbers, 47 is there. That embedding layer convert this 47 into 32 length vector implicitly. This one also convert into 32 length vector. This one also 32 length vector. So that fixed length vector, we will convert it. Fixed length vector, we will convert it. Now,
तो हम डिसाइड कैसे करेंगे कि कैसे कन्वर्ट करना है किसी भी नंबर को, क्योंकि हर नंबर अलग अलग कन्वर्ट हो जाएगा ना.
yeah. Embedding layer implicitly doing that, ma'am. How much length we have to decide through hyperparameter tuning. But what are the values it will take it? Implicitly it will take it.
Okay, we don't decide how
Maybe it will follow some procedure, like it will take numbers, okay? Maybe in binary format, maybe it will convert it, okay? Maybe binary. Suppose if you want to represent a number, suppose 1024, how can we represent it? 32-bit. First to 20 numbers are zeros, next number is 1, remaining all zeros. Like that it will convert it. It will follow some procedure based on the here in the coding. See, here we are importing this embedding. Maybe they defined some procedure how to convert the number into numerical vector. It will follow that procedure. I'm not going in that level. So you see here, in first epoch, see total 64 in each batch, 64 sequences are there. Total
your screen is not visible.
Yeah. I'll share. Praveen sir, are you there? Praveen sir. Right. So now see, total 25,000 sequences we took. Each batch 64 we took, total 391 batches it came. Batch by batch it's running. Now first epoch completed. What is the loss? 0.47. What is the accuracy? 76. 0.76 means 76%. See, training accuracy is increasing, loss is decreasing. Come to validation. Validation accuracy, you see, first time we got 85%, 87, 85, 87, like that, fluctuating. Right now, training accuracy, if you see, training accuracy is very high, validation accuracy is less, just training. So we will go that, we will see later. Now first, yeah, come to questions.
Actually, in that 5,000 samples, how many were chosen for train and how many for test in this example?
No, we are taking sentences. See, sir.
Okay.
Yeah, that I'll give clarification. Just wait, sir. See, whiteboard. Actually, what we are doing, we are taking 25,000 sequences. Okay, 25,000 sequences means 1 to 25k, and this one last 50k. We are taking 25,000 sequences. In 25,000 sequences, each sequence contains some words. Okay, that word maybe comes in top 5,000 or not, we don't know. Okay, in training set also, in test set also, some words not comes under 5,000 rank. Okay. Some words comes under 5,000 rank. That 5,000 ranks words, it will come in train set, it will come in test set, not a big deal. Okay.
Okay.
Now, any questions, sir?
Sir?
Yeah, this yeah, tell me, ma'am.
Can you please explain the concept of sentiment classification again?
Sentiment classification?
Yes.
Yeah, this we are doing now, ma'am. Sentiment classification means this is one type of movie review classification, whether movie is positive or negative. Sentiment classification means suppose uh, sentiment means whether the person is positive about that thing or negative, that we are doing. Suppose I
Okay.
purchased a product like laptop. So laptop speed is very good, everything is working well. I purchased for a high cost, everything working well, I'll happy, and then I'll write a positive review. Suppose someone purchased the same laptop but he's not satisfied with with its performance, he'll write negative review. Okay.
Yes.
Same way how movie review means it contains words. Again we follow same procedure to convert each and every word into numerical vector. First we will give ranks. Word wake is there, word to wake conversion. That word wake, what it will do, if you give any sentence, for each corresponding word it will convert into some numerical vector. Okay. But what we are doing here, we ourselves giving ranks to words, and based on that ranks we are converting, embedding layer converting into numerical vector. Each word is converting into numerical vector. So same way we can do it, whether the review is positive or not, whether the person is positive opinion on that product or not, where it is useful in real time. The companies can analyze the data. So more positives are there and some negatives are there. Okay, company wise, okay. If more negatives are there, then company needs to rectify. Okay, what are the problems are there in that product? They need to rectify it, right?
Okay.
So for that purpose, it is useful.
Okay, sir. Understood. Thank you.
Can you
Thank you.
summarize, sir? I'm requesting you, please summarize it, because few minutes starting, I'm not able to attend it. And summarize vector, how to convert it into summarize vector. So kindly once just summarize it.
Which
I'm
one, sir?
requesting you.
Which one? Only this.
Sir, initially after first 15 minutes, I was not able to attend.
Okay.
And you are already telling summarize vector, how to convert into summarize vector. Please just summary it.
Okay, total PPT. In PPT, sir.
Yes.
Sir, better. We will share recording, sir. I'm getting resound actually. So see, first what we discussed, sir, in this presentation. First, what are the disadvantages of CNN? I discussed. Then what are the limitations of CNN? I discussed. Then I go and discussed this RNN. What is RNN? Please mute it, everyone. Please mute it. Yeah. Someone, due to some echo, I'm getting my voice. All right. Need of RNN, where RNNs are useful in sentiment analysis, time series data, machine translation. Machine translation means from one language to other language. Speech recognition means if you send some audio, how from that audio how we can convert into text. Image captioning, if you give any image from corresponding that image, from that image our machine will predict some words or will generate some words in image captioning. Now what is the core idea of RNN? We discussed. Then we will go recurrent neural network, how recurrent neural network work at different time instances, how it will take input and how it will generate output, how the current state output send to next state. All these we discussed, sir. Now long-term dependency problem we discussed. If some output is depending on the previous inputs, how can we predict that? That we discussed. Why RNNs are not solved long-term dependency problems practically. To overcome that, we go for LSTM. That LSTM we discussed here. And different types of RNNs we discussed. Now in RNNs, different variations of RNNs we discussed. How can we train RNN? We discussed here. How can we train RNN? Now we discuss different types of RNNs, variations of RNN. Now we discussed about LSTM. So I'm not going in detail, but these topics we discussed in recordings. You listen, sir, once. Now, see, after completion of 10 epochs, so we got train accuracy is 0.96 and validation accuracy is 85%. Now you just try to print it, the accuracy. Any questions, sir?
This in sentiment analysis also, do we compute this loss and accuracy?
Obviously, sir. Everywhere we will find loss and accuracy. But here we given metric is accuracy.
Okay. Okay.
How we will decide the size of the padding?
Yeah, sir. Someone asked question.
Sir, how to decide the size of the padding? It is 600
Yeah. That is a hyperparameter, sir. Size of the padding is hyperparameter. Previously, how we decided number of epochs, how we decided batch size. In the same way, we decide embedding length. Yeah, tell me.
Once we have trained the model, how to test it with real-time data, sir? How to pass real-time data to it?
So previously we saw, no, sir, how can we test in IMDb? I'll show that code also once. Please give me.
And step size. Step size. So when I say 10, 20, step size as 2. Okay. So the range function, what it will do, it will start at number 10. Okay.
Oh,
It
sorry.
will go up to 19. 10, 11. Okay. Go.
Praveen, please
When I
mute
say
it.
step size as
Please
2,
mute
it will
yourself.
go in the steps of 12. That is, it will take 10, 12, 14.
Praveen, sir, please mute yourself. IMDb, where I given. In MNest, I shown, sir, how can we test it? We can write, yeah, this I'm not getting. Maybe in other mail it is there. Yeah. Evaluate. See, like this. Model.evaluate, X test and Y test we will give, and we will find it. With this sentence, we can do it.
Okay, sir.
Right.
Thank you, sir.
So, yeah, next resource person is going to join. So I have another meeting. Please, I'm leaving. So SAR will explain you, I think, applications in
Sir, please share your Python notebook in.
everything I'll share today. Okay.
Thanks, sir.
Okay. Thank you very much. Praveen sir, are you there?
Yes, sir.
For every
Yes, sir.
index,
Yeah. So I'm leaving the meeting, sir.
how many elements are present
Thank you,
here?
sir.
5
Thank you
and
very
all.
much for your valuable session. Very good.
Okay, sir.
I request the participants, we take 10 minutes of break. Later, sir, Damodar sir from NIT Goa, he will continue the session.
Okay.
Praveen sir, I'm leaving the meeting. Okay.
Print all the.
Sir, you can leave, sir.
Thank you. Thank you.
Thank you very much, sir.
Now we
Thank you.
can use else with for loop also. Yeah, I think it's.
I request the participant, please take 10 minutes of break.
Yeah, I think, okay. Sorry for that. Some of the friends were speaking to. Now it's gone, I think. Okay, right. Yeah. Yeah, just like you use else with while loop, you can use else with the for loop also. It's like optional thing. Okay, it's same thing, right? I'm iterating to all the elements. If all elements are over, Yes, it increments automatically. Yeah, it retracts, right? Okay, so yeah, so this is the part. So this is the optional part, just like I explained it in the while loop, right? Okay, now let's see the program of displaying all prime numbers in an interval. While loop, what we did, we try to check whether the given number is prime or not. Okay, now with the help of this for loop, we'll try to display all the numbers in between given range. Okay, the code is similar here. I mean, you can see here what I'm doing. So I want to print all the prime numbers between 20 and 10. Okay, so I want to print prime numbers between 20 and 10. Okay, this index one value will be placed here. This index two value will be placed here. That is formatted. So when how it pretends? It pretends like prime numbers between this index one value is what 20 and 50. Like that it will print. Okay, I'm passing the index values here, like, so it's a way of formatting. So what I'm doing here, see, I'm taking the combination of loops here. You can see here, if you observe here, I've taken the combination. I'm using the for loop and I'm using some if block here.
Yes, sir, it's started now.
Yes, now it is started. So I'll share the slides again. Okay, now today's session we are going to see the various applications of machine learning and artificial intelligence. We just take a case study on human-computer interaction and then we'll try to discuss. Now you see, when you are investigating any problem in any domain, tell me what is the main problem you face? Somebody? Because many of you are, I'm sure, working in different areas of your expertise. Tell me what is the main problem you have faced in your respect? The first problem, or you could say, the first problem. The moment you.
Sir, as per my
yes.
As per my knowledge, sir, how to take data and how to train it and normalization sometimes, and we should understand how to take input and output so that we can get our result or we can get a best prediction.
Yes.
We should first understand our model, what we require.
Yes. So here in this process, like you mentioned, the first one you encounter is the data. Do you agree with me? The moment
yes, data handling is crucial thing. Sometimes big data is there. How to process it.
First time the availability of data itself, that I mean the problem you're going to face in the very beginning of your research, right? If you take any domain, some wireless sensor network, some computational biology, some other domains, cloud security, some other network, wherever it is, computer networks. The moment you choose, you are in search of some particular data set that is required for your application you're going to investigate, right? So other domains, wherever you are doing, you have the main problem of data availability. Once data is available, only then you will be able to develop some suitable model for the data and then implement the model on data and get some simulations, plot it, and then write a paper, right? So in this domain, in this process, when we feel that data acquisition is very, very difficult, if you go with these type of domains like some human computer interaction type models, when we are developing some systems, we are developing the hardware or software models, here the advantage is we are going to have this first the data that we really require. So once the data is available, somehow you get some model and get into some implementation and you'll write the paper. So the designing part, you can do it accordingly. So the first and foremost advantage of this domain is I'm going to have my data available with me, right? Now I'll go to the next slide. Can you see the slide that defines the human computer interaction? Please confirm. Yes. So please let me know if slides are not getting moved. Sometimes in full screen mode it won't happen. Now I'm going to take a case study in today's session. Like I have a domain, some human computer interaction where I'm going to make an interface between a computer and a human. Then I'm going to understand what type of data I'm going to record according to some selection application. Then I'm going to use some machine learning model, some advanced artificial intelligence model for the selected application, right? Now, can you tell me what exactly we'll get by way of interfacing this one? If we make an interface between a human and a processor or machine, tell me what we are going to get. Somebody guess, please. Somebody guess. What are we going to get here? When we make an interface, you get some data, right? Can you give me one example of similar application? Any one example? One example. Somebody? Okay. Now see, when there is some medical issue and all, we used to go to some hospitals and we used to perform certain diagnoses and all, right? Now I want to ask anyhow, I will come back to machine learning applications and models that are required for this particular domain of purpose. But just let me know when you have a particular problem of similar kind and go to some hospital and get some recordings done. Maybe it's the ECG or EEG or any other type of data. Now let me know, is it a kind of human computer interaction model? It could be maybe a BP machine or some ECG machine or some EEG machine or any type of system. Is it not a kind of human computer interaction system?
Yes, sir. Yes, it is.
Yes. So everything that interface between a human and a processor or a machine, that makes the HCI system, and the outcome is certain type of data. Now my question is, what type of research I can investigate with this type of systems? Somebody give me an example now. Any one example, like I am making an interface between a human and a particular processor or a machine, and I would like to solve some real-time problem. Give me one example, you tell me. Any one example.
No, even for example, if you take some calculation of taking an algorithm from the machine and
Yes.
with the data you gathered, suppose I wanted to know the mean or mode of that. So, I mean, just uploading that table and maybe we can get result using machine algorithm.
Okay. Any other simple application, something like somebody's voice recognition, somebody is giving some other. Can you give me any one other example? Simple example.
Or translation, sir. For example, linguistics. Here you have put one word, linguistics.
Yes.
Maybe
Yes.
translation also. Google Translator I use.
Yes.
That is also through interaction with that this only. No?
Okay. So now let's take a simple example. Now I'm going to take some ECG data. You know, right? ECG data, what it takes, like if somebody is giving Alexa, yes, kind of example for human computer interaction. Now I would like to take some ECG recordings of the heart functioning, right? So ECG tells how your heart is functioning and how the basic, requirement of this one. And you're going to make some diagnosis and understanding something, right? So can it be possible, like if I take some ECG recordings and I plot these polygraphs and all, then I'll make some analysis using some statistical and machine learning model. Then I will say the person is likely to be, having certain complications with his heart, or it is perfect. Like again, of course, it's a classification problem, like healthy or some particular problem with the heart issues, something like that. Maybe it's a binary classification, like healthy, not healthy, or you can say any risk for cardiac arrest may happen, something like that. So when you can interface and get some data, next task is what? Suitable machine learning model to be applied on the data. Using data, we are going to make some understanding of the type of application we are into and investigating, right? Yes, somebody is answering prediction, obviously. For example, somebody is already attacked with some heart attack or cardiac arrest. I'm going to make some prediction out of this one, right? Some prediction I can make, how likely is going to get a cardiac arrest me the next six months or 1 year, and what is his current state of functioning of the heart and all those things. Prediction models, yes, eventually you can develop. Any other simple application, like is it not only heart related or any other type? If I take the brain signals, EEG signals, then based on those signals, I can make some understanding of the personal behavior classification, mental state analysis, human contemplation, and many other type of applications, based on which I can see, I can simply say a person is lying or not, or what is the mental state analysis of the person. Nowadays, if you see most of the companies, before giving the offer letter, they may have the person to undergo for this type of psychometric type test, where we can see the behavior of the person, whether he is genuine or honest or maybe good or bad. All these personal classification, personal behavior classification can be taken care using these things, and many other applications. But of course, where do we use machine learning? We can use everywhere. Of course, the moment we can make an interface here. The moment data comes to you, you have to find this. Now you can't choose everywhere arbitrarily some models. Tell me what type of models we can adopt heavily here. Tell me. The moment you go for this type of interface, tell me what type of models you require. Is neural network or fuzzy logic or any other genetic algorithm type models, or any some swarm-digest model? Tell me. Somebody guess, tell me, for these type of models where I'm going to make some neural network. Yes, I think Kalyani, somebody answered. Yes, neural networks. Why? The reason is here we have the advantage of training. I can train my model. Like for example, if I go with lie detection, I train on some 100 patients. Like if the person is answering like this while the recordings are being happen, when you are recording the EEG signals, then you can say so and so happening. Then we can say that what the person has, is lying or not lying. When you it's exactly like your supervised learning models, right? And similar way, if you have developed a model based on some kind of diagnostic tool that takes the data of the diabetes related information, then what will happen? The data the model you are investigating on some 100 patients, and you are making the classification like somebody is diabetic or non-diabetic. If somebody is diabetic, and what are all the parameters you are considering? Somebody is non-diabetic, what are all the parameters you are considering? Accordingly, you can go for understanding this. Then okay, let me take a case study here. Let me take a case study just for understanding. And see, now I'm going with some brain signals that I'm going to collect based on human-computer interaction. I'll use some system to connect the brain signals, and based on those signals, I'll try to understand how this model is going to work. Now tell me, using brain signals, what and all I can perform? You tell me, just in one line. Some applications, like if I know your brain signals, tell me what and all the applications I can perform. Anybody, just one example. Controlling anything.
So,
yes,
like lie detection, in lie detection.
Yes, that's well known. Any other than that?
Health. It is also neurological health, maybe one aspect of the brain signal analysis.
Yes, we'll understand the cognitive behavior, the neurological functioning of the person. Any other?
Maybe IQ, indirectly IQ level, or the responses.
Yes, IQ, because IQ refers to the human brain and all those things. Yes, you're right. Now,
emotional quotient, emotional behavior, or whatever.
Yes. Mental state analysis, personal behavior classification, all those things. You see, just if you go with one interface like this, see how many applications on this part you have given about 10 applications, all of you. Still, many are writing that. Now, other than these conventional applications and all, if you go with any if you go with some privacy related application and so on, so now I want to read some personal privacy information from the human brain, because like when you say somebody is lying or not, I want to understand how they are doing so. So I would like to get some brain signals and say that whether it's what is the inherent information in the brain signals. I just want to fetch the information. Is it possible? May not be exactly possible now at this point of time, but the research is ongoing heavily in this domain, where maybe in near future we are going to understand and get some better idea how to make or extract such information from the human brain that will be useful. Just for just understanding, I want to know your mobile number without asking you. Okay, is it possible to get it? I think Sumana, is that ethical? Yes, I think you have the question. This domain has some ethical issues in the picture. Yes, because the moment you go with the moment we go for interface, you see now you take a Wi-Fi connection. The moment you have the Wi-Fi connection, we have our password with us, right? Otherwise, anybody can use it. So the privacy issues, once it is open to everybody, people will try to misuse that, right? Similarly, ethical issues will be there. When ethical issues is come into the picture, security has to come into the picture, right? I hope you're convinced. Yeah. When there is advances, when there is any advancement of new systems, certainly ethical issues will come into the picture. People will always use it and misuse it. Whenever the people misuse it, we have the security issues to be there to protect them. That's the different side of the dimension, right? Now, having said so, can I get your mobile number without asking you? Without you sharing that? Not possible. Now, let us see whether at this point of time, can we go close to that? May not be. Yeah, you're right. Not possible at this point of time. But maybe we can get it. I will explain. Now, I will ask you, what is the first digit of your mobile number? Tell me how many possibilities we have. 10. Yes, 0 to 10. Maybe for first number may start with something 9 or maybe 9 possible. Usually first number mobile number never start with 0. But okay, just generally you ask me that some 0 to 9 possibilities. Second number some 0 to 9 possibilities. Third number 0 to 9. Total some 10 possibilities are there. Okay. First number maybe 9. Usually mobile number won't start with 0. That's fine. So now what happens for each number, if I ask you a question, like the person whom I'm taking the data from, the brain signals, okay? Yes, you are right, 10 multiplied by 9, but I'm going with digit wise, each digit wise. First digit, I will ask a question. I will ask you, what is the first digit of ATMP? I mean, this one, your mobile number. You will answer. You will answer some other zero. I mean, of course, you don't answer because you don't want to share that. But when you are thinking about the answer, like obviously you will come to know whenever I ask, is it 0, is it 1, is it 2, and so on, is it 9? You will definitely have match in your brain, right? Out of 10 responses, how many are positive or how many are negative? You tell me. Tell me. Yes, 1 positive and remaining 9 are negative, obviously. So is it not like a classification problem now? Because see, I have some 10 signals. Out of 10, 9 are one group, 1 is one group, 9 are negative class, 1 is positive class. Do you agree with me? Yes.
Yes.
So obviously, when we make such a behavioral classification of the human functioning or the brain functioning of a human, then of course you may feel, how can we exactly capture such signals and all? I don't say, I mean, impossible. It is possible, because even if you can smile a bit, there will be some reflection in your human brain, the signals. Even if you move your finger also, if you move your finger, there will be some change in your human brain, the behavior and all, the cognitive behavior. Therefore, it's not so difficult to identify or capturing or extracting such signals, which will help you to deal with this type of behavioral classification. So now, what type of signals I'm going to make and understanding this one? See, basically, I know how these artificial neural models are developed from the functioning of the biological neural model. All of you know, right? Artificial neural models, how they have developed and all. Now, how do you differentiate brain and the neurons? You tell me. Brain and the neurons. Now, see, the moment I say human brain, we have the advantage of what? We have the some millions or billions of neurons. They synchronize and they work together to perform a lot of tasks in a daily life, right? Of course, the functioning of the this neuron, it behaves. There is a cell body. There is a new. Of course, how the central nervous system works with the communication of neurons, and there is a neuron. Um, there is a nucleus. There is a dendrite. There is cell body. There is soma. There is dendrites. All those things. Axon, hillock. All those things. How do they synchronize? Because I'm not going to teach how exactly the biological neural model works, because already you know, all of you know what is the biological neural model, how artificial neural models are evolved. But here, when the concept of brain comes into the picture, how the neurons communicate each other and how do they perform a particular task in synchronization with the neuron communication, and then how there is something called action potential. If you perform something, there will be some action potentially generated in human brain. And usually, if no, spinal cord abridges the communication all over the body via the muscle receptors and all. So accordingly, when the neurons communicate, these electric signals are being generated. Okay, because usually the neuron signals, they jump from neuron to neuron at like 250 miles per hour with that speed. Now, when with such speed, when some signals are being captured, I mean, when such speed the communication is going on, some signals are being identified and captured. Those signals we are going to use for the, because the moment we go for human computer interaction, we have to understand in depth how the communication is going to happen, how we are going to understand these signals in what sense. Because somebody is lying, there is a different behavior comes into the brain. Somebody is laughing, somebody is crying, somebody is sleeping, obviously. So you have to understand the basic structure of the human brain. Only then you will be make these changes. So, like I said, at the moment you go for making some interaction with some part of the human body, you have to understand at least the domain knowledge, basically. If your case study is like brain-computer interface, you have to understand the basic structure of the human brain, how it functions, how it performs operations and all those things, how it synchronizes with the spinal cord and other muscle receptors, how the neurological communication is being processed and all. And if you're going with some heart type of problems, diagnosis and understanding and prediction, then you have to understand the basic functioning. Only then what is coronary artery, what is the these different rooms of the brain, and then how the how the heart functions, how it synchronizes with the brain, liver and kidneys and all those things. All this basic. Only then you'll be able to make the recordings of the appropriate location, right? So now if you see, I'm going to anyhow discuss how the machine learning models and all those things, when it comes to the proper definition of this brain computer interface. But if you see each of the region of the human brain, we have different responsibilities and all going to happen. We have one region is for emotional control, one for language processing, and one for some spelling of words. Some because there are basically frontal, parietal, occipital, and temporal lobe. There are 4 different lobes are there in the human brain structure, right? So here, I'm not going to teach the basic, biology and all. You can read on your interest in case you are going with this type of case study. Please confirm meanwhile whether I'm audible or not.
Yes, sir. Audible.
Yes. Now, see, I have choose now in other domains. First, what you do? First, you go and understand the basic prerequisites, some preliminaries. Then you will read some topic. Then you will get a problem statement. Then you. But this, when you go for human-computer interaction, first you understand the problem or the application which you are going to investigate. Whether I'm going to go my application is lie detection or some human contemplation or behavior classification, mental state analysis, IQ analysis, some smart IoT applications like some wheelchair, smart wheelchair or smart prosthetic device, retinal prosthetics, other robotic arm type application, whatever it is. First, define the application, then select from those locations where you're going to get these signals from related to the chosen application. I'm going to follow lie detection. When you're lying the data, see previously when the lie detectors are being used, they are using like pulse rate, skin conductance, and blood pressure, heart rate, and many other parameters, right? But now the moment we can say lie detection, mostly it should be referred to the human brain itself because it is the brain that is lying, not the other parts of the human body, right? Similarly, fMRI, because it is very important what type of application you are selected and accordingly what type of data you are in need. Only fMRI, like it detects some blood flow in the brain region accordingly, based on some emotions, based on some performance and so on. So obviously when there is some emotion, accordingly the change in the blood flow will be different, right? So accordingly, that's the kind of representation of the brain performance and functioning. Similarly, NIRS data we have based on some IR light absorption that is being placed onto the brain and other parts. And similarly, CAT scan, PET, and many other type of data we're going to investigate. But please, like somebody was asking just now, the ethical issues and all. Yes, mainly a lot of ethical issues are involved in this research. Using machine learning and all, you have free hands. But when you choose a particular application using some machine learning model, according to the application, I'm going to record some signal. Can we just give our brain data to anybody arbitrarily? We can't give. No, because if just someone comes and asks, I'm doing some projects on prediction of BP or detection of accurate blood pressure. Can you simply donate our brain BP data? No, we can't give because there are some ethical and other issues are involved here. Now, all those who are doing some research in machine learning using for such biomedicine or any medicinal application or any other type of application using these type of HCA models, please make sure that you have to follow certain protocols for recording and all. There is some ethical committee approval. There is some other parameters you have to follow up. Only then you will be able to understand. Otherwise, it will be very difficult to deal with this type of. There may be some complications at the end because you have to take permission from your institute ethical committee and then you also take to permission from all the subjects. If, for example, you are taking from 10 subjects, 10 people, the data may be brain signals or any other type of data. You have to take permission from everybody. Only then you will be able to use their data and should not be used for any commercial purpose. All those things are there. And if you see in the figure, there are some 4 to 5 layers that is shown in the this brain region before going to happen. First we have scalp, then periostem, skull bone, dura mater, and many other layers we have. So brain is located under different layers of structure. So if I want to select some application using human brain signals, can I simply reach to such a level and can we dig to such a level and get the recording directly by attaching the electrode to the human brain? No. Why? Because it requires some surgery and it performs some complex medical procedures and all. We can't do that. So that is actually invasive method. That's actually invasive method where you are going to record the signals from the human brain by directly opening the skull and then attaching the electrodes, but by just digging out all those layers. But on the other way, you can use non-invasive method where I'm going to record the brain signal directly by attaching the electrode to the human brain. The scalp onto the hair, of course. Okay. So now here, every such, for example, if we're talking about this particular human-computer interaction model, where I'm going to take the BCA signals, the brain signals, there is an amplifier. Why there is an amplifier? Because basically when the EEG signals are identified, the signals are nothing but the summed iconic type of signals where what you can say the currents of thousands of neuron communication or neuron signals are being captured. Therefore, such a signals have to be amplified maybe some 1,000 times, 10,000 times, because sometimes the quality may not be so accurate that you can capture so easily. So there will be an amplifier to get the quality of those signals. I'm going to show those hardware devices now, of course. Then the brain computer interface and all, the basic definition I will define. Before that, how the entire system can work and how it is being used. See, if there is a subject, if you are using for some some lie detection or forensic application or anything, there may be a patient, a subject or a patient, the one whom you are taking the data from. So once you take the brain signals, or any other type of recording, whatever you are making, then this BCS system will process those signals captured and then make some proper classification techniques and other type of implementation models we use. And finally, the front end, we used to apply this some smart device, like fine, all those things. So basically, like we can develop a controlling device, maybe for some smart wheelchair or prosthetic application where the signals of brain are being captured and used for the selected purpose, right? This is how the entire system look like. If you see, we are taking the signals from a subject where the data is being taken. Can you see the entire setup for the communication system of human brain structure? Can you see the figure?
Yes, sir.
Yes. Now, if you see, there is a subject where I'm going to take the data from. There will be an amplifier where the signals, the capture signals are being amplified, and those signals are stored further in some external devices, some storage devices. Then there is some feedback mechanism or some system will be there. Based on that, again, now it is not like that one subject I'll take once in a while the data. No, subject 1, trial 2, trial 3, and so on, multiple trials of data. And again, next subject, again, trial 1, trial 2. So it is like a multi-dimensional validation we are making over the data sets. Why? Because if your model works better on one person, may not work on different person. It work on one person for one instance, may not work on different time, because the person behavior classification is different from time to time. Therefore, from subject, different data trials, each subject, then different trials I'm going to have, like then multiple subjects. Okay. And of course, there is one easy control to look after the entire communication, and that makes the connection with the EEG amplifier. Okay, this is how the type of communication is being happen normally. Now tell me, where do we use exactly the machine learning model? See, once the signals are captured from the amplifier, and then the desired signals are stored in the external device, we can use for some pre-processing models and all there. Then we can use this some classification models. Once the feedback is taken based on that, again you can train the model or train the subject, and again you can make the similar type of recordings up to some finite number of trials. Okay, so once the display signal is captured and pre-processed, then we are going to use the machine learning models accordingly. Okay, yes, how to remove the noise? Now see, I will come your question one after the other anyhow. Somebody is asking how to remove the noise. Obviously, you see, when you go for this type of experimental setup to be purchased, mostly it comes with the customized tools of software we have. Like the EEG amplifier with, for example, here we have some 16-channel EEG recording system where we have, there is a tool for, brain vision and analyzer and recorder both. So first we use the recorder software to record the signal, then analyzer software to use for some, pre-processing and other type of models, right? So either way we used to deal with. So pre-processing can be done. There are some lot of filters we have, and there are some existing models we have. Or if you can develop your own model of your choice using some machine learning models or any other, even for pre-processing also. Like I said, that there are many, customized software tools we have to have. for classification and other type of purposes. And if you go with some biomedicinal application, how we are going to use this type of human computer interaction system. There are multiple such models. We have neuromodulation type of problems, type of techniques, where we have three type of deep brain stimulation and TMS, transcranial magnetic stimulation, and we have vagus nerve stimulation. Of course, those who are into some computational biology and bioinformatics side applications and biomedical signal processing applications type. And so basically, of course, but this requires some kind of collaboration with some medical practitioner. Otherwise, it is difficult to deal with these type of data sets. First of all, getting the data is very difficult. Because in this type of modeling, we are going to place an electrode inside the human brain structure, and we are going to use the data that is recorded from the electrode, and there is an artificial, chip where we are going to store this type of data. There is some a battery pack that is deployed inside the human body, and of course, complex surgery you have to perform. This is not for normal data collection or operation. Mostly, we use it for some specific diseases like epilepsy, stroke, and any other type of diseases, just to operate or make the region active that is not working fine. So if you see, like there are some experiments are being carried out to make the persons who are not very active or drowsy and many other complications they are facing, to we try to make the magnetic pulse to release or ease the depression, with the help of which the person can become active. And so what we can do here, we can make the SAM models that to record the signals every day when the treatment is going on. We can see the clear picture or the improvement in the treatment or in the patient by way of the treatment. Okay. So how this magnetic energy is going to reflect and going to affect your human brain functioning. Accordingly, we are going to prove that. This is just a recording that you can do when the treatment is going on. But again, to prove that, again, you require all the machine learning models, some deep learning architectures, some other architectures. Now, if you see, there is some prosthetic device that you can, this is one of the, important application we can use it here. Tell me, how do we use this type of application? See, the moment we choose to design a prosthetic device, first we need to understand what type of device we are making. But is a robotic prosthetic arm type application, or is the one that is shown in the figure is a prosthetic leg? Okay. Of course, there is a huge difference between this prosthetic and the normal prosthetic, which has no processor at all. Tell me, what is the main difference here? Is the comfort and efficiency. Comfort and efficiency. Now you can have these type of artificial prosthetic devices to be developed with the help of these brain signals connected from the human brain. If it's the missing limb, the muscle receptors cannot carry forward the action potential that is being generated. Therefore, you may have to carry forward those signals from some, of course, electrodes, and those electrodes, the signals, when they are captured, you're going to process them in such a way such that the classification of those signals done. When the left leg is moving, the right leg will move accordingly. But of course, this requires a lot of synchronization and all, because getting it working like a normal leg is not so, so because you have to see such a level of functioning of the human brain architecture. Okay. So this prosthetic device is one of the very important and wonderful application where people are currently investigating on. Not only this type of, even we have retinal prosthetic and prosthetic or robotic arm type applications. And then, in fact, the same type of logic you can use for robotic robot navigation, or you can say some other robotic application for game playing and multi-user game programming and all, where you can synchronize your brains with the processor of the robots and all who are playing the game. Then you try to make some kind of communication with them. Accordingly, you're going to control the devices, something like that. Not exactly like a fiction movie that what we are going to discuss, but exactly this is in a different way how we are going to solve this. But problem is the processing, real-time processing, taking the feedback from the system, then reprogramming and error sometimes. They are all the problems. Similarly, we have retinal implants. How we are going to make the fixation of the particular chip with the help of which the captured images can be sent into the optic nerve, which is directly connected to the human brain, and how the brain can read this information. How are you going to deploy such a complex hardware inside the human skull or close to the human brain proximity? That's not so easy. Of course, they all require a lot of complex operations and all, where you require to collaborate with some medical practitioner or some specialist. Okay, but if you get data, you can prove that their accuracy and efficiency, right? So there are some problems that are happening with the neural prosthetic devices, which will help you to understand these type of problems. Now tell me, what is the main problem? Like, see, the speed of information transfer. If you take, if the information speed is not so high, not so good, then see, if the left leg is moving one, right leg is moving 2 times or once on the other way, then that won't be a replacement, right, for a prosthetic device. And similarly, position where you are placing the electrodes so that they capture the valuable signals or useful signals, because you cannot switch off, you cannot switch on the light and expect the fan to move, right? So similarly, we have to understand the position of the channels are very, very important. The position of the electrodes, because if you place the electrodes at a wrong position, accordingly, what happens? You're going to get wrong signals. Okay, your job is for some light detection to take data from something else. It may not synchronize properly, right? And there is some feedback delay. If there is some delay with the feedback, accordingly, there will be some error in the program, some error in the implementation. And similarly, there is some poor signal quality. Sometimes the position of the electrode is good, but the signal quality is not so good. Sometimes we have amplifier, but sometimes amplifier, if the signal quality is not so good, what an amplifier can do, right? So all these problems can be there with the neural prosthetic devices. There are some people who have already used these type of prosthetic devices, and then they have successfully carried out all these regular activities. And somebody who has a paralyzed patient has used this type of prosthetic device with the help of which she has participated in some activities. And if you see, like the concept of EEG signals or any other, not in the recent days, long back we have seen there is some electric field that is being featured about the human brain structures. Why? And they try to see the kind of data observance long back. But now it has come into the picture. The reason is now with the increments of this big data analytics, where you're going to see a lot of human machine learning models, and the concept of using those signals for a better purpose has become possible now. That is the reason that people are focusing on the old wine now in a new bottle. Okay. Now, if you see, can you see this slide? States of vigilance, EEG states of vigilance. Yes. Now, see, before going to do any such domain, first, please, we have to understand that you have to understand that what are the benchmark behavior. Maybe it's a brain signals or heart signals or whatever it is. You should understand the benchmark behavior. Only then you will be able to map to your problem, right? So, like somebody is alert, what type of behavior comes from the human brain? Usually, brain releases beta waves, right? Brain releases the neurological signals processing. What do we make? Those electric signals, they come, they produce beta waves. Then, similarly, when somebody is relaxing, we have alpha waves. When somebody is sleeping, we have theta waves. When somebody is light sleep, we have different type of, see, all these signals, they are of different nature, you see. Similarly, when somebody is in deep sleep, we have delta waves. When somebody is in paradoxical sleep, we have REM. Paradoxical sleep, nothing but somebody is dreaming or not. Of course, why you may ask why. Just I'm giving an example of sample benchmark. Right? Similarly, there are many. Don't think only these type of behavior comes from the human brain. There are so many type of signals as such are existing, which we need to understand and select according to the application that we are going to investigate. Are you following me? So it's very, very important to understand these signals. Somebody is alert, whether beta, somebody is relaxing, alpha waves and all, subject to the application, like, right? For example, I'm going to record the signals of a particular player who is going to play the game. When he is playing the game, he should be very alert, beta waves we have to see. When he is relaxing, he has to have alpha waves, something like that. Now, if you see somebody is in paradoxical sleep, like dreaming, we can have REM signal. Now, can anybody say that whether you had a dream the last night? No, only you can say that, right? But can you say what time you have had the dream the last night? Can you say, anybody? No. Why? Because hardly you can have that. I had a dream. You can remember that. You sometimes we don't even remember which dream we have had, right? But here, what we can do, if I connect the electrodes to the human skull or the scalp onto the head before we are going to the bed, and when we sleep, if the moment we start recording our observance of these REM signals, then we can eventually understand that okay, the person has started dreaming that. So next day we can say that you had a dream, and what time you had a dream, from what time to what time. Use just for your understanding, I'm telling, it's not exactly the application we're going to investigate. I'm not going to make some dream analysis and all. Just want to say that different type of behaviors are being captured using this NIHCA model. Okay, it's very important to understand all of that. Then see, each of these type of signals, they have different type of lobes we have, like, I mean, there's some ranges. Like beta, we have 13 to 30 hertz of signals, alpha 8 to 13 hertz, theta 4 to 8 hertz, delta waves 0.5 to 4 hertz and all. Mostly beta waves occur in frontal and parietal lobe, alpha waves occur in occipital lobe, theta waves occur in children or sleeping adults. Of course, it could be anywhere. Any doubts? Somebody is speaking?
Whatever it is, we'll discuss in the class.
Pardon?
So Nivedana, just wait. There are many people struggling with the second program itself. Okay? Just wait.
Any problem with it?
Problem, sir. No problem.
I think somebody is speaking in between. Please turn off your microphones. All of you, those who are not, I mean, those who don't want to ask any doubts, they can please turn off your microphone. Unless you have doubts, no, please don't turn on your microphone. So, like you understand now, because it's not like they just connect one electrode wire and get some signals and use them for some real-time purpose. No, not like that. You have to choose what type of application you're investigating, and for that application, what and all the signals or waves you require, and what are their frequency and ranges, and then which are the lobes they are going to be extracted, and then what are the experimental protocols we have to define for that. They're all to be understood properly. So there are many people who have used this type of human-computer interaction applications, like some patients and some other biomedical applications users and all those things. Now, if you see the entire operating environment, starting from the recording to the application. Now tell me, what is the application that we are investigating in this slide? Just see the slide and tell me what is the application we are investigating here.
Controlling wheelchair, sir.
Yes, we are going to make a smart wheelchair, some smart IoT type device. They integrated with a smart wheelchair or with a wheelchair that makes the wheelchair functioning better. And we don't require somebody to control that on our mini. We can just control using some. Assume that there is a locked in or a paralyzed person or immobile person who cannot move or walk. And maybe we can develop such a sophisticated system by taking the signals from his human brain who is sitting onto the wheelchair. And then he can control his emotion. I mean, he can control the wheelchair with respect to or based on the brain signals that is going to be captured accordingly. We have to understand. So how it happens, the BCI devices, we have the attachment of electrode onto the human scalp and the user. Then we emit with this one, those signals are captured, and the amplifier will give you the digitalized signal, and the feature extraction will be used for extraction of better features, and then some feature translator, of course, to make the classification. And then there is some control interface, and whatever the whatever the extraction of the information you want to do from the digitalized signal which are pre-processed, and those after classification of the signals, you are going to control the wheelchair by just making a device controller. There is a device controller between the control interface and the device. Okay, based on the classification and the extracted information and the knowledge discovery happens from the pre-processed signals of the human brain, we're going to control the device, like move left, move right, move forward, move back accordingly. If you see that Krishna movie used to control the something with only 2 fingers. Similar way, we're going to take some recording from the human brain. But you may ask, if the person is paralyzed, how can we take the signals? Brain is not paralyzed, right? Brain works normally. In fact, the persons who cannot move or walk, and sometimes who is like blind, sometimes the brain functioning is better than the normal persons, because they have to depend everything on the human brain, right? So this is the entire operating environment, how we are going to perform various operations, and then getting the data, and extracting the signals, and then digitalizing the signals, pre-processing, classification, then analysis, then device controller. Finally, that smart wheelchair will work according to the signals of the human brain. Are you following me? Then we have this entire, this entire phases of this one. We have the brain signals come from the human brain. Then after signal acquisition, that there is a digitalized signal where some signal processing operations are being performed, some feature extraction, translation. Then the commands are being issued for some BC applications. Okay, so maybe smart wheelchair or any other robotic arm application or anything. Okay. So in computer science, mainly they deal with like developing some new feature extraction method or some classifying, development, designing some efficient classification models, and then some noise removal models, and then many other some filters they can develop to deal with the signals and all. There is some electrical and electronics type researchers, they can work on investigating the hardware devices used for this purpose, and we can produce or develop or design a better hardware for signal acquisition and pre-processing. And similarly, we can work on adopting to some smart or some useful applications of real time. Now, like I mentioned, we have to understand the usage of some standard behavior of the human brain. The moment I go for BCI as the tool for this one, you have to understand some complex benchmark behavior. If you take this P300 speller, basically what happens, this used to recognize in the brain in terms of a stimuli, it exists only in relation to specific output. Means if I see something already, if I see it again, sometimes you will see the presence of this P300 stimuli. Okay, so this is basically what happens if I use it for some application like some forensics and all. Can tell me where exactly I can use this? Some P300 speller. If I see an object, yes.
So is it like sixth sense or what?
Pardon?
We say like sixth sense or what? Like
No, not six. See, if I see something, like see,
okay.
I'm a stranger for many of the participants. If they see me, because
Yes.
they don't know me, there is no P300 speller present in their human body. It's a kind of wave, right? Some
Okay.
spike. So if the people whom I have seen already, or whom seen me already, who noticed me already,
Yes. Then.
if we record the signals, and we can understand that at that point of time, if we record the brain signals, we can capture similar behavior from them, that P300 wave. Now tell me where exactly I can use these type of spikes.
I thought so that sixth sense one. Sorry.
That's fine, but where I can use this type of brain behavior? I'm talking about any sophisticated method.
Okay.
Not tell me where I can use this type of behavior. No, I'm interested, like there is some data. There is some data that we are going to record. I'm telling this data can be used for so and so purpose. Now tell me, can you give me one application where I can use this? Anywhere?
Maybe lie detection type.
Yes. Can you just any little elaborate? See, assume that there is some crime happens. There are some 3-4 persons are suspected. I think somebody answering face detection. Yes. People recognition. Yes. You can use for all these applications. Now let me give a simple example. If there is a crime happens, there are some 3 to 4 persons are suspected. Now what happens, if you can show some related information of the crime, like crime scene photos, weapon used, person murdered, and then many other details of the crime. Then if you ask the person whether you have seen this particular instance of time, I mean instance are the objects or the items, photos and all those things. If the person is intentionally lying, but if at the same time, if you notice the P300 spikes in his human brain, then what happens? You can use that information and you can conclude that the person is lying. Means what, the person must have investigated. I mean, must have involved or helped in the particular crime. Something like, not exactly, just some rough idea I'm giving in for some digital forensic applications and all. Do you agree with me? Because when we can develop such a behavior, obviously we can make these type of mappings, right? Not exactly for lie detection type, but similar like this. Some forensic application where I can make the investigation of similar type using this type of behavior. Okay. But now again, you can ask whether we can capture such signals. Yes, obviously. because brain region has more than 250 channels and all. We can record different type of signals from all over the human, all over the region of the human brain, from different lobes, like 4 lobes we have, temporal, parietal, occipital, and other lobes, parietal. So I'll just give that similar example now. If you see, there are various channels are shown in the actually not all shown, only few of them are shown. I think about 30-40 channels. If you see the bottom figure. Now tell me how many channels are highlighted here?
4.
4 channels are highlighted. Why? The reason is, for my application that I have, like I mentioned, first you have to choose the application here. For my application, some T7, some T8, some P7, some P8 channels of these 4 would be sufficient to get some signals of them, so that I can get some statistical analysis, some machine learning model, some deep learning, so on, so where I can make the classification using these 4 channels. I can say, what is my classification? Here, if it is lie detection, you have binary classification, like what? Guilty, innocent. Guilty, innocent. Guilty means lying, innocent means not lying, something like that. It's a binary. Again, of course, the moment I say binary classification, you must think of SVM and all other type of classifiers, right? But here you can even better, because sometimes we require a lot of training of these signals and all. So SVM may not work better here. SVM will not give any type of training, right? Any sort of training much here, right? Are you following me?
Yes, sir. Yes, sir.
In a similar way, we have, but that's why choosing the appropriate channels for recording such signals is very important. So if you are working on some application where you have T78, P7, P8 is required really. If you go with some F1, F2, some FC1, FC4, something like the different channel, and it is something like you have lost something somewhere and you're searching for searching somewhere. Obviously, you have to choose the appropriate channels for recording the suitable brain signals, right? Accordingly, you are going to understand the behavior, suitable behavior. That is known as the cognitive behavior for the chosen application. Okay. So as I already mentioned, there is a different type of EEG rhymes we have, subject to the nature of the type of data and subject to the different constraints how we are going to record. And similarly, there are some game playing type application. If you see, the person is imagining that cursor is being moved towards the target, and then how we are going to mentally visualize the cursor to go to the target, and then how the cursor is moving towards the target and all those things accordingly. And so just the person will just imagine that he is growing certain direction, like some reference point here. I'll just simple logic, 1 2 3 4. If I imagine 1, it will go forward, 2 back, 3 left, 4 right, something like that. So see, if I have these 4 operations like left, right, front, back, I can move anywhere, right? Diagonally also. Do you agree with me? So if you can make such an imagination of the game playing, and the person can conveniently move towards the target without any interface with a keyboard or any mouse. So such just a game playing application I'm giving an example, not all. Then similarly, we have non-invasive type BCA applications which we are going to investigate. If you see that one, the one is shown in the top figure. If you see that the one that is shown in the figure is the easy cap. That is actually the location. First you fix the easy cap, then the channel location are shown there. Green color channels, blue, white, and many other channels are shown there. Okay, yellow color and all. So the channels will define different type of meaning or behavior of the human brain structure. Okay, but this is non-invasive. You're not going to make any surgery here, right? It is cost effective and no implantation, and of course no much noise also. Sorry, here there may be a lot of noise, because non-invasive technique normally contain a lot of noise, because there are a lot of layers of extraction required, and then sometimes external noise may be there. So you require a lot of filters to be used, and many other some noise and artifacts can be used here. Okay, and what happening right now? You see, there are some wearable EEG devices which you are going to use here. Are you following me? Now the one that is showing just like your some wireless headset, right? So it's, now tell me how many channels we have here. If you show in the figure, how many channels we have there? Yes, some 5 channels we have. 1 2 3 4 5. It means what? At a time maybe you can record a maximum of 5 channel data, right? At a time up to, but which channel and all, which you can reach by moving them, by just moving towards upward and downward. You can find what are the channels you can reachable. You can reach those channels, you can record, but at a time maximum 5. Okay. And similarly, there are different other devices we have. This is single channel neurosky device. And now tell me how many channels we have there in the one that is shown. Single channel. This is a single channel EEG neurosky device which you are going to investigate for some real-time application. But the advantage is they are wearable channels. They are wearable EEG devices. Okay. Normally be used for some patient monitoring system, developing virtual patient monitoring system, personal behavioral analysis, or surveillance system. I just want to see type of applications. Similarly, you have distributed game playing using some virtual and augmented reality applications where I can have a wearable EEG device like this. I can control the players in the game, or I can control as an admin, and multiple players can play the game by just controlling the visual thoughts into that. Okay, but this comes under a similar wearable device application. Now, future, what is going to happen in future with this type? What is the future scope? Like I mentioned, so many applications I have given. Many of them are already started investigating. Some application people started doing using, I mean, recently some machine learning models, something like measuring the IQ of a person. Yes, virtual reality games you can use it, and in fact you can develop some smart device where whatever you can imagine in your screen, it can reflect onto the what you were imagining inside, that can be plotted onto some real screen, something like that. Of course, in a virtual and augmented reality environment, and controlling some other neural processing devices and all those things. Many other applications. Of course, security and privacy issues will obviously follow, because this type of high-end research areas obviously will have this type of things will carry forward. Okay, so I think I've given enough information on this one. I'll just show the hardware equipment just for a while. Accordingly, you can see how we are going to use this one. I'll just show the equipment once. First, I'll show the single channel one, then followed by the multiple channel. Am I audible? Please confirm. Yes. Give me a second. I will show.
Sir, audible.
Can you see this single channel EEG data acquisition system? This one.
Sir.
Now see, what is this one? This one. Tell me, somebody. I've already explained in the previous slide. If you see, I can move this towards this side. I can move this and place the device according to the electrode position, and then of course it's a wearable device. You are right, somebody is answering. But now see, this is the electrode, this is the electrode, this is the electrode, and where it is going to take the data from at a time one channel of the human brain. Okay, one channel. Now the moment you place the data, it is like this. Either from you can just move it upward like this way. You can move it accordingly it can move it, and you can change possibly maybe here or FP1. I think FP2 maybe here. Fortunately, you can reach what another possible channels you can reach, and the data that can be transmitted over some Bluetooth or wireless any device. You have an advantage of transferring data over some Bluetooth medium. Okay, on real time. Okay, real time. Now this can be used for, like I said, some surveillance system, some personal behavior classification. It is just like I said, right? For example, there was a person who has undergone for some medical treatment and all. I want to make him some observation over him, and then for some surveillance type applications and all, I can make the person to wear this one and all. What I have to show this one? I'm already showing on full screen mode. I think you have to. Somebody is answering to show on the full screen mode. I'm already showing on the full screen mode, I think. If you want, I can show the this box where you can see this one. This is a single channel brain vision. This one starter kit. Brain vision. Okay. This is costing around, I think, 17,000 now, 18,000. It was some 12,000 rupees long back. Now it is costing some 18,000. Okay. No.
It be used in sports.
Yes.
In sports.
Yes, sports also you can use this type of application. You can see the type of analysis they are making, the type of strategy they are using, and not for just communication, only for recording and seeing the behavior class, how they are acting when they're pressure and all this. Some analysis you can make. Any application. What application I can't say, because there any application where you can take for which you require at least one channel. One channel data, exactly one channel data. If you require multiple channel data at a time, you cannot use this, right? At a time, you can take only one channel data. This, okay. So those who are the beginners, if they want to do similar type of research, maybe they can buy one such and they can use it. Okay.
Sir, is one sufficient for lie detection, sir?
No, because maybe what happens, you can't say exactly how many channels here, because we see when we are lying, we have seen the, like in the previous slide I have shown that T78, P7P, those 4 channels we have seen they are acting more when somebody is lying, because we have developed our experiment accordingly. Because first, for this type of done, you have to develop your own experiment. So we have developed our own experiment in which we have observed that these 4-5 channels are more active. Does not mean that others are not active. Now, if you have only one, if you are going with lie detection, then you have to first go for P7, then P7. But only thing is, actually, they are you may not reach all the channels from this one. Only it can be moved only in one direction, upward and this low, downside. Fine. Whether you can reach all this at a time, you can record one channel, but whether you can go to any channel once, that we don't know, because you can't reach, right? The hardware is fixed. So that's why you have to go with some at least 3-4 channels data. Okay. If there is maybe some other application which require at a time only one data, that is for particular channel which can be reachable, you can go with this one. It doesn't matter. But lie detection, because sometimes we have done, we experiment with 4 channel, then 8 channel, then 16 channel we went up to. Okay.
Okay, sir. Thank you, sir.
So those who want to start the research in such a human computer interaction system, what my suggestion is, they can go with the single, that lower cost one. You see whether you will be able to do, then you can go for higher version. That's my suggestion. Any doubts? Now I'll show the higher version, that is with 16 channels. Okay.
Okay.
Actually, it is supposed to be a practical session. Now I can't make the practical session, right? So, can you see this?
Sir.
Yes, sir.
This one is 16 channel. Like we have 1, 2, 3, 4 up to 8, then 9 to again 16. Total 8 plus 8, 16 channel. These two are the reference and ground. They are a must. They are must. So if I want to make an application where I require some 3 channel data, 4 channel data, accordingly I have to make this setup for me. Okay. If my application something like lie detection, if I involve, I require some 2 channel, 4 channel, then I will explain. This is not wearing. This is not wearable. This you keep on the table. Somebody is asking how to wear it. This is not wearable. What is it? You keep on the table. Keep on the table, and then take this electrode wires. Okay, I'll show you. Take this electrode wire. Okay, place this cap, easy cap. I've already shown in the previous slide that easy cap you have to place onto somebody's this scalp. Then after placing there, just place it like that. Then connect this electrodes. Just fix this electrode like this. Just fix it. That's all. It is fixed. Then the subject is ready to give you his data for you. But only thing is, when you are fixing here, you have to apply some electrode gel here. This one. electrode gel. This electrode gel you have to apply, with the help of which you will be able to get some better quality signals. Okay. So this is how you fix onto the scalp, and then you require, now this easy cap size is 32. This is 32 channel easy cap. If you see all this channel 1, channel 2, channel 3 and all, there are 32 channels we have. At a time I can take maximum 32. Now tell me what is the size? 16 channel. This is 16 channel amplifier. This is amplifier. Okay. This is 16 channel amplifier, using which I can take any 16 of this one. Any 16 of these particular channels available in the human brain, right? But which 16, it could be anything, because I have the electrode well flexible, I can connect everywhere, right, out of this 32, right? Are you following me? So this is not variable. Somebody is asking how to vary it. This is not variable. You place it on the table, then connect the electrodes wires. How to connect? I'll just now here how to connect to the amplifier. I've shown how to connect to the scalp using the easy cap.
Sir, but at a time I can use only 5 channels, right, sir?
5 by 5?
You have told it is a 16 channel.
No, 16 channel. If your application require, like you are doing some lie detection or some behavioral classification, if you require data from 16 places of the human brain, assume that at a time, then all 16 you have to keep, plus 2 extra. These reference and ground must. Okay, ground connection and then reference, like for which you are taking the data from, like. So 16 plus 2, 18 total required. If your application involves 16 signals at a time. Okay, like that. See, connect the wire here, on the other side you connect here. This is placed on the human scalp. That's all. Okay.
There is no problem with hair, sir, while we are scanning the signals.
No problem. You are going to many lab tests, right? Some blood test you are going, BP, like that. This is just a recording of your brain signal. Nothing will happen. The only thing is you have to apply little gel, this one, that electrode gel. Now this gel, when you are applying, this is Amul box, so don't confuse this. Just for easy carrying, I have to, actually there is a bigger box. For carrying, I have used this Amul box. Don't confuse with this. So this electrode gel you have to apply to the hair. After recording, you should request the subject to wash his hairs. That's all. It is like a shampoo, not harmful. Okay. It is just recording his brain signal. Already that is used to fetch all over the time. Only thing is signals are being emitted all the time. You have to just record them when your turn comes. That's all. Okay. So this is recording. The moment now, see, now where see from the human brain, you through these channels, from the wires which you are connecting here, from the wires it is reaching here, going inside the amplifier. Then the amplifier signal you are going to connect to the computer from here. I've shown, right, the entire operating environment. How we are going from the scalp to the easy cap to the electrode wire to the amplifier to the some workstation or system to the hard disk. Then from there you go to all your MATLAB, and once that file is converted to a .m file and all, your Python file you can use wherever you want according to your requirement. Okay. So this is 16 channel human computer interaction system. Okay. So you have to have as many electrodes wires as you require. Okay. All are expensive. This electrode wire is expensive. This gel is also expensive. Any other doubts you have? Actually, it is a fully practical session. Now we can't show, right, here. Like normally we used to call a student or somebody, we used to request him to give some data. Then we used to connect all these electrode wires. Then we show the brain signals in real time. And you will see when somebody is laughing, when somebody is crying, when somebody is closing the eyes also, we can see the difference, clear difference. But now it is not possible, of course. I think we are done. Any doubts? Now I'll leave for 5-10 minutes doubts. If you have any doubts, you can ask me.
So is machine learning useful for fraud detection too?
Which fraud detection?
Like those happening in bank fraud or something like that.
Once you come up with some lie detection model, you can experiment in such a way that see, it is, what do you mean by lie detection? You just bring a subject, connect these wires, and make some recordings and ask the subject some question. If you see some movies now, how do they make the recordings? What is your first? They start with what is your name, where do you work, and all. Then slowly they will come. Similar way, you make some investigation and then you start recording the signals whenever you are in need of that.
Okay.
Actually, subject training is very important. You cannot call him and directly start recording. Subject will be tensed and you will not get a proper accurate signals. A lot of other practical and technical problem. Ground reality is different when you are going for lie detection.
Okay. Thank you, sir.
Any other doubts? You let me know.
Yes, sir.
Please tell.
In one slide, you said It is HCI is human computer interface. In one slide I saw.
Ah.
And another side it is interaction.
See,
One
basically
side
what
it
we are
is
making
interface.
is,
Is there
yes,
any
yes,
difference?
yes, difference is there. See, interaction,
I was
interface, there is a
confused.
difference.
It is interaction.
Yes, see, it is like a communication device. Not exactly, just you just try to understand. Interaction means what? There is some communication going between these two. Interface is what? You are making this particular, setup that is required to make these interactions possible. Are you following? By means they can be used interchangeably. Both are same, but when the moment the interface, it is little higher. It is not generalized. Interaction is a generalized. The moment it's the interface, you are creating a medium, some transfer medium, which will help to make these interaction possible. So interface is a setup, I can say. Interaction talking to the communication, but more or less they can be used interchangeably. Any other doubts you have?
Thank you.
Let me know.
Thank you very much, sir, for your valuable session.
Right. Thank you, sir.
Thank you very much, sir.
Right. So if you still have any doubts, maybe you can send me an email.
Sir, I need 16 electrodes for the 16 channels, no, sir?
Yes.
Yes.
Yes, sir. Normally, when you buy, they give more electrode wise. Okay, now you do it 16, they give 20, 30 extra. That's fine. You can use for 16 channel application. You require 16 plus 2, totally 18 you require.
Okay, sir. Thank you, sir.
Right. So any other doubts, you can contact me. All my details are available in the NIT Goa website. That's all. I wish you all the best. I would like to thank the organizers for giving me the opportunity of interacting with the participants.
Will you share your email ID, please?
Yes, I am posting now.
Okay, sir. Thank you for the great session.
Yes. 1 second. Huh? I posted my email ID is dr.reddy@nitgoa.ac.in. Please get in touch with me in case you have any doubts. Thank you.
Thank you, sir.
All the best, all the participants. Thank you.